Okay, so let's look at some of the problems in the textbook. Let's start with the first one from number 20. Number 20 says, given that complex number, write it in polar form. So this is in rectangular form or standard form. Let's write it in polar form. Okay. Well, if we're going to write it in polar form, then it has to be in this template. And cis, remember, is this shorthand for cosine of theta plus I times sine of theta. And your textbook does not use that shorthand. It writes out the answers in longhand. Okay. So, first thing we need to do is to graph this complex number in the complex plane. So the complex plane is just like the rectangular plane with x-axis and y-axis, but instead of a x-axis we have the real axis, and instead of the y-axis we have the imaginary axis. And so the real part of z is 2, and the imaginary part of z is the square root of 3. So we can think of this as a point, and the point, so in the complex plane, this is a point with coordinates. Well, the real part of this is 2, and the imaginary part of this complex number is the square root of 3. So, if 2's about there, and the square root of 3 is 1.7 something. So the square root of 3 would be about here. That's where that point would be. Okay. Now, we need to find r if I'm going to get this in polar form. So r, by definition, is the distance from the origin to our point. So that's what our r is equal to, that distance. But we saw in class that it's also the modulus of z, which is the square root of the x-coordinate, or the real part squared, plus the y-coordinate squared. So that's 4 plus 3, which is the square root of 7. So put that up here. We can refine this. Okay. Now, if I want to find out what theta is, well, theta is this angle here. Okay. So I need r and theta to put this into standard form. Sorry, into polar form. All right, so what I'm going to do is I'm going to now draw a triangle, a right triangle, that we make when we form this. And so I'm going to have that out here blown up. There's my right triangle. Okay, and so what I have here is my angle theta. Okay. This side is r, which is square root of 7. And this leg, well, it has height square root of 3. And then this leg has length positive 2. Okay, so this is that right triangle that I have. And so I can find out what theta is. I can see here, if I label this, that's my hypotenuse, that's my opposite side. So I know that sine of theta is equal to opposite over hypotenuse. And so I have that. And if I want to find theta now, I can just take the inverse sine of both sides. Now, the instructions on these in the textbook said to give your angle in degrees. So just make sure that your angle, your calculator's in degree mode. So those will cancel, and I'll get what my angle theta is. Okay, so I'm going to do that now. I'll do it somewhere where, so I'm going to come here to mode, and we might make sure you're in degree mode. Okay, and I'm going to want second sine and square root of 3/7. Close parentheses for square root, close parentheses for inverse sine. Now angles, if we're not told how much to round them to, we generally take them to 1 decimal place. So that's 40.9 degrees. And now I can complete this. It's going to be the square root of 7 times cis of 40.9 degrees. That is the polar form of, trying to get this off, that is the polar form of this complex number z equals 2 plus the square root of 3 times I. So if you look this up in the back of the book, well, I've given the solutions to all of them, odd and even. It has it written in longhand. Okay, but as I said in class, we're going to use this shorthand. The book doesn't use this shorthand. Okay. All right, so there's that one. Let's do a new one. Let's look at number 19 from your problems in 10.4. So suppose z is equal to this. This is in standard form. It's a complex number. So let's write z in polar form. Okay, so I'm going to draw this in the complex plane. So in the complex plane, z will be a point, and the x-coordinate is its real part, and the y-coordinate is its imaginary part. So in the complex plane, this is the real axis, that's our imaginary axis. That's where our point is going to be. Okay, now let's find the polar form is going to be r times cis theta. So let's find r. R, by definition, is the distance from the origin to our point in the complex plane. So that's what r is going to be. Also, by definition, r is the modulus of our complex number z, which is the square root of the real part squared plus the imaginary part all squared. So it's going to be 9 plus 16. And so my modulus is 5, so r is equal to 5. So I can refine this. Okay, so this distance is 5. Okay. All right, so the next thing I need to find is what my angle theta is. Well, the angle theta is this. So that's going to be my angle theta. I need the reference angle. The reference angle. So we don't have to worry about a reference angle when you're in the first quadrant because the reference angle is the same as your angle theta. But here, that's going to be my reference angle. And so I'm going to form a right triangle. I'm going to make it a little thicker. Okay. So now I'm going to make that larger out here. There's my right angle. And this side is 5. Okay, we just found that r is 5. This is my reference angle. This point has coordinates 3, negative 4. So this distance is 3, and this distance here is 4. Right. So again, if I want to find out what my reference angle is, well, if I label this, there's my hypotenuse. With respect to the reference angle, there's my opposite side and there's my adjacent side. The sine of my reference angle is going to be opposite over hypotenuse. And so if I take inverse sine of both sides, then these will cancel each other out, and I'm going to have that my reference angle, and my reference angle is in the first quadrant, so whenever I'm doing inverse any trig function, I'm going to get the answer in the first quadrant. Okay, so we have that. And so now I'm just going to put that in my calculator. Inverse sine of 4/5. And make sure it's in degree mode. So inverse sine of 4/5, close parentheses. And if I take that to 1 decimal place, that's 53.1 degrees from my reference angle. Okay, so now I'm going to take my calculator away. But I need theta. I don't need my reference angle for this. In polar form, I need theta. And as you can see here, a full revolution is 360. So we go a full revolution around and we subtract out our reference angle to get theta. And when I do that, 360 minus 53.1 is going to give me 306.9 degrees. So this is my theta, and so now I have this in polar form. It's 5 times cis of 306.9 degrees. And that's my answer for that one. Okay. Again, in the book they give this in longhand. So 5 times cosine of 306.9 degrees plus I times sine of 306.9 degrees. All right, and then for the last one on this video, I did number 21. So if z is this complex number, then write that in polar form. And write your angle. The instructions for this set said to write your angle as in degrees. Okay. So we're going to have to find r, and we're going to have to find cis theta. Well, let's, if we graph that in the complex plane, we get the point whose whose x-coordinate is the real part, and whose y-coordinate is the imaginary part. Okay, so I'm going to have -2 comma 3, so z can be thought of, so this is my real axis, that's my imaginary axis. And now I need to find r. By definition, r is the distance from the origin to our point in the complex plane. That's need to work out that distance r. And by definition, r is equal to the modulus of z, which is the square root of the real part squared plus the imaginary part squared. So that distance is equal to the square root of 13. And so this will be the square root of 13 times cis of theta. And we need to work out what theta is. Okay, for this example, theta is an angle in quadrant 2. Okay, so I need to get the reference angle. This is our reference angle. Reference angle is the angle formed from the terminal side of an angle in the nearest x-axis. So if I can find out what the reference angle is, then I can get theta, because theta will be the flat angle, which is 180 degrees, minus the reference angle. Okay, so I'm going to form a right triangle. And then I'll make it bigger out here. So there's my reference angle. And we have that r is the square root of 13. Now this point here is -2 comma 3. So this side has height 3, and this side has length 2. Okay, so if I label this, okay, I can just take, I can see that the sine of my reference angle is going to be opposite over hypotenuse. And so I'm going to take inverse sine of both sides. And so these will undo each other. So I'll get my reference angle is the inverse sine of 3 over square root of 13. So that's what I'm going to do now. So second sine 3 over square root of 13. And press enter. So to 1 decimal place, my reference angle is 56.3 degrees. And so my angle theta is going to be the flat angle, 180 degrees, minus my reference angle. And when I do that, I'm going to get 300 and, sorry, let me do that one more time, 123.7. So we can check that. 180 minus 56.3 is 123.7. So I come here. That's my angle theta. That's my answer. Okay, now again, if you look this up in the back of the book, it's going to tell you that it's r, and in longhand, times cosine of 123.7 plus I times sine of 123.7. Okay, but this is the shorthand. Okay. So in web work, they may not, they don't use that shorthand. So you're just meant to put it in there in the longhand unless you're told otherwise. All right, so that ends this video.